So in this video, this is section 3.3, page 187 in the text. I'm going to work out problems number 29 and number 31. They're very similar, so I want to work both of them out with the same video here. 29, we have f of x is x to the 1/3 plus 1. And so this is going to be pretty straightforward. We're going to do this first derivative analysis, find the intervals of increase, decrease, and find any relative extrema, if there are any. And so we have f prime of x, the derivative is 1/3, x to the negative 2/3. The derivative of 1 is 0, so that vanishes. I'm going to rewrite that as 1/3 x to the positive 2/3. That's going to become a little clearer here. All right, so we need to find the critical values. And we need to find type 1. That's where the derivative is equal to 0. Now, remember, our derivative here is a fraction. So setting a fraction to 0, for our purposes, that is equivalent to setting the numerator to 0. So a fraction is equal to 0 anywhere the numerator is equal to 0. And then we also need to find where the fraction is undefined. The fraction is undefined anywhere the denominator is equal to 0. So type 1 critical value, set numerator to 0. Type 2 critical value, here in just a moment, set the denominator equal to 0. And so if we set this numerator to 0, we get 1 is equal to 0. Now remember, if there is no variable, there is no solution. Remember that no solution does not mean wasted time. No solution means whatever you're looking for, there isn't one. Because if there had been, we'd have found it. What were we looking for? We're looking for type 1 critical values, and there are none. Okay, wonderful. There are no type 1 critical values. Go ever upward and onward here. Type 2, that's where the derivative does not exist. I'm not writing this down because I have extra marker to use up. You need to write this down every time. You need to write that down every time. If you want to get full credit out of me on the exam, then you stinking better write it down every time. There are over 1,000 places in the U.S. where you can take Calculus 1, and if they don't want you to write it down, God bless them, they can do whatever they want to do. If you want full credit out of me, you're going to write this down every time. So type 2 critical value, that's where the first derivative does not exist. And so we're going to set the denominator to 0. So this is 3x to the 2/3 is equal to 0. Divide both sides by 3, so that vanishes. And then raise both sides to the 3/2 power. It's not very hard to see that x equals 0 is what makes that expression true. So we have only one critical value. It's where x is equal to 0. So we have divided the number line into two pieces. A short little bit here. Someone might reasonably ask, what if you look for critical values? What if there are none? Some functions don't have critical values. If that happens, then you still have the number line divided into pieces, but you've divided it into just one piece, the entire number line. Here, we need to choose a representative value from both regions. I'm going to choose -1 and 1 because they're the simplest to use. Here, you need, it would be a different problem, obviously, but here you would need to choose a different critical value from one of the regions. Well, you can choose any critical value you like. You might as well choose x equals 0 or x equal 1. You can choose x equal anything here because they all give you the same result. So however many critical values you generate, you just use whatever you inherit from your work. In this case, we inherited one critical value, so there are two representatives to work with. We need to evaluate the derivative at each of those numbers. And so I'm going to define f prime at -1. I'm going to find f prime at +1. I'm going to use this version of it. If you want to use a calculator, that might be easier, but it's all the same. Calculators sometimes have a little bit difficult time with 2/3 power, but it's pretty straightforward if you're just working this out. This is -1 to the 2/3. That means you square it, which becomes +1. Then you take the third root, which is still +1. 1 times 3 is 3. So by hook or by crook, this is 1/3, which is, for all we care about, is bigger than 0, which means the function is increasing here. All right? And then f prime at 1 is even easier because 1 raised to any power, any finite power, is equal to 1. So this is still 1/3, which is still bigger than 0, which is still increasing. So it's increasing and it's increasing. Well, this is easy enough, so we just simply say, so f is increasing, and it's increasing on the interval from -infinity to 0, and it's increasing on the interval from 0 to infinity. My recommendation is this: do not combine consecutive intervals. Do not combine them. This is correct. If you leave them not combined, it is correct. If you combine them, sometimes it's correct and sometimes it isn't, and we don't want to, and believe me, you don't want to go through all the considerations as to when you may and when you may not combine them. The simplest thing to do is, it's increasing here, it's increasing here, so just let sleeping answers lie. That's correct, let it be, there it is. So f is increasing on both those intervals. Those are the intervals of increase and decrease. In this particular case, it turns out, yes, you may combine them, but that is not always the case, and so you should not. The best advice is not to combine them. Now, are there any relative max, relative min? Well, the only place you can have a relative max is if we have a critical value at A. If the function is increasing here and is decreasing here, then yes, there might be a relative maximum here, and you would need to check to investigate that. If the function changes from decreasing to increasing, then there might be a relative minimum here, and you would need to check to see if you have one. Since this particular function never changes, that means this particular function cannot have any relative max or relative min. There are no relative extrema for this function because it never changes from increasing to decreasing or vice versa. So there's problem number 29 worked out, and that's our final result. And there we have it. So next up, I'm going to work through number 31. It's going to be similar. Of course, it's not exactly the same, but it's going to be very similar. Number 31 is, I believe it's x plus 2 to the 2/3 power. So f of x, this is number 31. Priest Holmes played for the Kansas City Chiefs, number 31. Also, the great Brett Saberhagen for the Kansas City Royals, number 31. F of x is x plus 2 to the 2/3 power. And so we need the derivative. So this is the chain rule. So this is 2/3 times x plus 2 to the -1/3 times the derivative of the inside, which is 1. And I'm going to rewrite that so it's a little more user-friendly. This is 2 in the numerator, 3 in denominator. This is x plus 2 to the 1/3 in denominator. There's a 1 in the numerator, but that's multiply, so it vanishes. So that's the derivative. And we can find the critical values. All right, so type 1. Type 1 critical values. So that's where the derivative is equal to 0. A fraction is equal to 0 anytime the numerator is equal to 0. 2 is equal to 0. If there is no variable, that means there is no solution. Remember, no solution does not mean wasted time. No solution means whatever you're looking for, in this case, type 1 critical values, whatever you're looking for, there are none. So there are no type 1 critical values. Type 2. Type 2 critical values are where the derivative does not exist. That's where for this fraction, that's where the denominator is equal to 0. So I take 3 times x plus 2 to the 1/3, and set that equal to 0. Divide both sides by 3. Raise both sides to the third power. And then subtract the 2 across. So by hook or by crook, we get x equals -2. So there's only one critical value here at -2. So this is my number line. Choose representatives from each of those regions. The simplest are probably going to be -3. You could use 0 here. I think actually -1 turns out to be much easier. Oddly enough, -1 works out to be easier than 0. It's because this thing works a little more nicely. So now we're going to do our garden variety first derivative analysis. Need the first derivative evaluated at the critical values. I'm not going to change my color this time. F prime at -3, so here's the derivative here. So this is 3 times 3, -3 plus 2. Okay, let me make that a little bit nicer here. -3 plus 2 to the 1/3 power, which is 3 times, this is -1 to the 1/3 power. And if you need to use a calculator, that's fine. That's just the third root. Remember that third root, the negative sign is retained. Third root, the negative sign is retained. And so this actually works out to be -2/3. And for our purposes, all we care about is it's less than 0, because the derivative less than 0 means the function is decreasing. So in this interval, the function is decreasing. And then same song, next stanza. So this is 2/3 times -1 plus 2 to the 1/3 power, except this time this is 2/3 times 1 to the 1/3. 1 to any power is 1. 3 times 1 is 1, so this is 2/3. The fact that it's 2/3 is irrelevant. Oh, it's got a fraction. It doesn't matter. All we care about is bigger than 0, which means the function is increasing. And so in this interval, the function is increasing. We have a potential minimum there. So let's write our result here. We say f is decreasing on this interval, which is -∞ to -2. And we say f is increasing on this interval, which is -2 to infinity. We have a potential minimum, so let's see if the function is defined there. It might not be, so we compute the function value at -2, because if it is, we need to express our result as an ordered pair anyway. So f of -2, that's the original function, and here's why -2 is handy here. Well, that's going to be for the original function. It happens to be 0. And so this is -2 plus 2 to the 2/3 power. And so 0 raised to any non-zero power, finite power, is that's 0. Which is defined. 0 is a number, so yes, this does bottom out. It bottoms out at 0. So this is there is a relative minimum at our value is -2, 0. So those are our final result of problem number 31, first derivative analysis.